I am still grading the tests. Things are coming along and I should be done pretty soon. Grading is just incredibly taxing for me. It's not an easy thing for me specifically, so it takes me a while, and I do apologize for that. Things are looking fine. I just need to finish up the last page or so for everybody. And then, as a reminder, midterm grades go out Friday morning, and your midterm score for this class will have that test factored into it. It's just a check-in for your current average. And since I need to have the tests finished and input by then, we will spend Friday looking over the test. I'll put my answer key up on the board. We can talk about some things I noticed about each question, make sure everyone understands what was going on. For today, and for however much of Friday we don't spend on test review, we're going to continue with Chapter 5. We began it last week looking at the formula for work and at least two different forms of energy. We're going to continue that today, talking about converting energy between at least two different forms. Next week we'll conclude Chapter 5, and so the Chapter 5 assignments are currently listed as due on the 24th. Anyone have any questions before we continue on today? All right. Let's see. What slide did I leave off on? So, as a brief review, we talked about at least two different forms of energy in an amount of detail last time. Went over the formula for work. In order to do work, you need to use energy, or you give energy to something else as you do work on it. So I lift this object, I give it GPE, and then that energy remains stored in it until it falls. We will be continuing to study energy, looking at different forms of it, how it converts in and out of various forms, back and forth between at least two different types. First type that we're going to look at mathematically is kinetic energy. This is the energy of motion, and the formula is simply KE equals 1/2 times mass times velocity squared. We haven't used it yet, so quick sample calculation. Two objects are currently listed on screen. We have a 5,000 gram bowling ball rolling forward at 3 meters per second, and we have a 100 kilogram human walking forwards at 1 meter per second. Which of these two cases has more kinetic energy within them? So, who wins in case of having more kinetic energy in this case? Almost. A wins unless you remember all of our formulas need kilograms instead of grams. So that was a trick on my part. Again, general rule, every formula needs kilograms. That includes these new ones. So rather than inputting 5,000, you'll actually input 5. If you did not make that conversion, So let's just say you don't convert it to kilograms. Let's say you input 5,000 instead of 5, then your total answer would be 22,500 joules for the bowling ball compared to 50 joules for the human. Does that make any kind of sense? Now, it's not impossible to give that much energy to a bowling ball. It would just be rocketing off towards the sunset at a much higher speed, frankly. Use this again to kind of help get an idea for the sense of scale for what your answers should be if you're trying to compare two things to each other. If you convert to kilograms first, you get a more reasonable 22.5 joules for the bowling ball. What this means is it actually takes more energy for a human to just walk than it does to roll a bowling ball, which, the analogy I was about to make didn't actually go anywhere. 3 meters per second is pretty quick. That's 1 meter per second is usually about average human walking pace. So this is the typical sort of in-the-moment energy expenditure for just most people walking around. Which means walking is actually more strenuous than tossing bowling balls if you do it for long enough. Questions about KE thus far? All right. Main thing to note about the formula, an object has to have both mass and velocity in order to have kinetic energy. This is different to inertia, where if you have mass, you have inertia, whether you're moving or not. Additionally, the velocity term is squared, so proportionally it is a little more important than the mass term is. For example, if you go twice as fast, that takes 4 times as much kinetic energy. This is why going faster and faster is always a greater energy expenditure than going slowly. This is why running tires you out. This is why cars use even more gas going at higher speeds within a certain gear. Fast takes energy, unfortunately, more than it does to go slow. Like exponentially more, unfortunately. The other form of energy that we've begun examining is gravitational potential energy. This again is, of the two, it's the weirder one. This is energy stored in an object's ability to fall. Whenever you lift something, you're doing work to give it energy. It still has that energy until it is no longer at that elevated point. When something at an elevated point falls, the energy it has is released, usually in the form of kinetic, so it picks up speed until it hits the ground. So the higher you lift something, or the heavier it is, the more energy it takes to get it up there, the more energy it has stored within it until it falls. Formula is just mass times 9.8 times height. This is another one of those times where I install an absolute value bracket, because this particular formula doesn't care about the direction of gravity, it just cares how strong is gravity. So, similar sample calculations. 2 more objects. Well, and just objects. Case A, we have again a 5,000 gram object being lifted by 10 meters. And case B, a 100 kilogram, object being lifted by 10 centimeters. So, which case has more GPE within it? And what observations do you make in order to, do you need to notice before you can successfully do this one?
What was the question?
Which case has more GPE?
The bottom one. Don't you have to convert?
You do have to convert, and I was extra tricky this time. There's two conversions here.
I see.
5,000 grams needs to be put into 5 kilograms again. It's lifted by 10 meters. The 100 kilograms is lifted by 10 centimeters. So we have to put one dot there and one dot there. This makes our final answers 490 joules for case A, and I believe 98 joules for case B. Now, again, for a sense of scale, case A is 10 meters. That's about 33 feet. So this would be carrying a box up a flight of stairs to about the 3rd floor. Actually, maybe the 4th floor. Because 1st floor is at 0, 2nd floor would be 10 feet up, 3rd floor would be 20 feet up. So up 3 flights of stairs, let's say that. Meanwhile, this amount of energy, bless you, 100 kilograms is a mass a human could have, and 10 centimeters is about 1 stair. So this would be the energy needed to lift yourself up 1 stair. Not a whole staircase, just 1 stair. If we put 10 meters here instead of 10 centimeters, then that would be the energy needed to get yourself, or at least a 100 kilogram person, up 3 flights of stairs. So it's all relative, and here, since one variable isn't squared, the mass and the height are kind of equal importance. Doubling one doubles the answer. How do you guys feel so far? Okay. Now, we have formulas for 2 different forms of energy, and they are both forms of mechanical energy, meaning that it's relatively easy for one form of mechanical energy to convert directly into another form. All forms of mechanical energy have to do with motion, either motion that's currently happening or motion that could happen. That's why both KE and GPE count as mechanical forms of energy. Whereas something like chemical potential energy in your food is something different because it's stored and could be used for other things, namely heat. Now, various forms of energy can all be converted into other various forms. We're going to stick to mechanical though. And a primary, specifically when talking about mechanical energy, well, no, rewind. I'm stumbling over my words. It feels like a Monday. All forms of energy can be converted into any other form of energy. That is a blanket rule. And there's something known as the second law of thermodynamics that says that the total amount of, no wait, Second law is entropy. First law of thermodynamics. My mistake. First law of thermodynamics says that energy cannot be created or destroyed. It simply converts between different types and changes what object possesses it. This 490 joules, by carrying this box upstairs, this energy had to come from somewhere. It doesn't just manifest when you bring that object upstairs. If this calculation was to find the energy it took for yourself to carry something up those stairs, then this amount of GPE that's now stored inside whatever you were carrying, that energy came from somewhere. Namely, if you're the one carrying the object, it came from your body. You had that energy in you, you used it to get the box upstairs, and now it's in the box until it's not on that story of the building anymore. First law says that all energy, no matter what form it's in or where it comes from, can't be created or destroyed. The same total amount must remain from start to finish. We refer to this as energy conservation. So if all energy is conserved within a certain system, then the total amount of energy in that system at the beginning must remain to the end. Whatever action you are undertaking, total amount of energy in every single part of the system being everything involved in the process. If the process is you carrying things up the stairs, and the system would be you and the object you're carrying. All of the energy that is in the system before the change or the process occurs must equal the sum of all the energy that's still in the system after the process is finished. So this is the mathematical form of the first law of thermodynamics. Total energy initial equals total energy final. And this is the energy across all forms in every single part of the system. For simplicity's sake, we're going to focus on just different types of mechanical energy within each part for right now. But and you know what, I'll label it. Giving things names helps. First law of thermodynamics can also be called law of energy conservation. When I say that, I'm referring to this starting point for the energy involved in a question in a system where some action is taken. Any questions before we look at an example that utilizes this? Okay. Now the two forms of energy that we now have equations for are KE and GPE. So I'm going to talk you through a scenario where one of those forms would convert into the other. We apparently have a bowling ball cannon. This particular cannon is going to take a bowling ball and launch it straight vertically upwards into the air. I never recommend doing this. What goes up must come down. But for the sake of mathematics simplicity, we're going to launch this bowling ball directly straight upwards. Now we've done problems similar to this before. We looked at projectile motion of something moving up and then coming back down. We did that with the Fantastic Four equations, the first four that we looked at in this class. And we could still use those equations to analyze this situation. All that logic that you learned, all those equations, still work. They aren't magically gone now. This is just another way of describing it, and I want to make sure this way makes sense. We're going to launch this bowling ball straight upwards. poorly drawn Looney Tunes cannon. And launch a bowling ball straight up. We know the mass of this bowling ball is 10 kilograms, excuse me. It is launched at an initial velocity of 4.5 meters per second, specifically upwards. We can also assume that this takes place on planet Earth. So gravity will remain 9.8. And we are going to calculate what height this bowling ball will rise to. What is the maximum height that it will reach, upon which it will freeze for a moment before falling back down. And again, the old way still works. Just want to make sure that the way of looking at it through energy makes sense. So, launching a bowling ball. The second the cannon is fired, what kind of energy does the cannonball have? The second you launch it, what form of energy is present in the bowling cannonball? Kinetic. It's moving. It has some velocity, therefore it needs kinetic energy that is allowing it to move. And up here, at max height, what is its velocity at the moment it reaches its maximum height? 0. That is still true. That is a still true assumption from the beginning of the course. Once you reach the apex for a split second, your velocity tops out at 0 before you fall back down. Therefore, how much kinetic energy does the bowling ball have up there for that split second? 0. It's not moving anymore. So, I'm now gonna start filling in how we're going to use the law of energy conservation to help analyze this. We need to look at every possible form of energy that the bowling ball has at the beginning. We're going to classify the beginning, the initial state, as cannon is fired, bowling ball begins launching upwards. So this is initial, this is final. On the initial side of things, there's only two forms of energy that we've talked about. We've determined that at the ground, at its initial launch velocity, the bowling ball has some amount of kinetic energy. So the sum of all the energy types present down here will include that kinetic energy. For the sake of simplicity, we'll just call the top of the cannon a height of 0, measure how much higher above the cannon this thing goes. And so if this point here is height of 0, how much GPE does the bowling ball have at the moment it launches? 0. It hasn't risen yet. If you freeze time at the exact moment the cannon goes off, bowling ball has velocity but hasn't risen yet. So it has a lot of kinetic energy, but none of it's transformed into GPE yet. So down here in the initial stages, we'll have a lot of kinetic energy and very little gravitational potential energy. So I'm filling in the blanks here to kind of mathematically show everything that I'm hand waving. Total energy initial is again the sum of every single form of energy that could exist in the cannonball. We know it's going to have some amount of kinetic energy, so filling in the formula for kinetic energy, 1/2 times mass times velocity squared, 1/2 times 10 times 4.5 squared. And I'm covering GPE just to build up the framework. It hasn't really gained any GPE yet because it hasn't risen yet. Again, this is before it starts rising, the moment it has its kinetic energy. So at our starting height of 0, the initial GPE term is just going to be 0. So that's energy analysis for the initial condition of the bowling ball. Any questions about the initial side of this? Okay. Now we're going to compare all that to what's going on at the final point, which is what we're going to call this point up in the air. Up here, final velocity is 0, and we've risen to some unknown height. Law of energy conservation tells us we have to compare the total energy initial to the total energy final. So we'll look at the same forms of energy, but analyze them through the lens of the data for the final side of things instead of the initial. So we're comparing the initial KE and GPE to the final KE and GPE. These would be based on the same mass, that doesn't change, but using the final velocity and the final height instead of the initial velocity and the initial height. As we've already established, the final velocity at that max height is 0. At that highest point, it freezes for a second. So at this maximum point, it doesn't have any kinetic energy. Instead, all that energy has transformed into GPE, which is the form it now has while it's up there. We don't know what that max height is, but we can solve for it. So on the initial side, we have a lot of kinetic energy. On the final side, it's all going to become gravitational potential energy. And we've demonstrated mathematically why GPE initial and KE final are 0. Questions so far? Okay. I'm going to simplify this a little bit. I'm going to remove the terms that are zeros. So ultimately it's comparing initial KE to final GPE. should be able to solve for that maximum height. Does anyone's math disagree with the final answer of 1.03 meters? So, as a general rule that you can just remember and use anytime, whenever something rises, since it has an initial velocity upwards, it has some amount of kinetic energy. And as it rises, its velocity drops and its height increases. So every single step higher it goes, its GPE rises, and as its velocity shrinks, so too does its kinetic energy, and they go hand in hand. Halfway up, half of the energy would have converted. At the final height, all of the energy would have converted. So, whenever something rises, when it rises and it's slowing down, like if it is a projectile, for all projectiles, KE transforms into GPE. And the inverse is true when something is descending. If you start up here, you have GPE, and it transforms back into KE on your way down. You pick up speed until you hit the floor, and you get lower and lower, so your GPE drops. So, for rising and descending, this is the relationship between these two energy forms. How does this feel? Okay. I want to at least describe the start of one that we can begin next time. We're nearing the end, and I know this one will take longer than 10 minutes to fully get through, but we can at least describe it. Even though this is not a case of falling, strictly speaking, it is still a case of energy converting between forms. Because as long as you are any height above the ground, you have GPE, and it turns into KE whether you're falling or just descending in any way, shape, or form. That can include sliding down a ramp. So at this starting height, when you're on a slide, you have GPE. As you begin sliding down, you pick up velocity because your GPE is converting into KE. The same way it would if you were just falling. Doing it on the ramp just kind of makes it happen more slowly and changes the direction of the velocity. But it still happens in the same way and in the same. The energy still flows directly from one to the other. So in this kit, in the version we worked all the way through a second ago with the rising bowling ball, KE turned into GPE. Here, it's the reverse. Starting GPE will turn into KE as you slide down. And the direction of that velocity doesn't actually matter. Notice here, the velocity pointed upwards and v rose upwards. Those are in the same axis. But here, when you're going down a slide, your velocity, like with all of our ramp questions, is parallel to the slide. It's not up and down like the height you're descending. That fact that your velocity vector is not within the vertical axis doesn't matter. Your change in height can be vertical and your velocity can be on a slant because energy isn't a vector. Something I haven't mentioned yet. I did promise you I'd tell you every vector, I'd make sure you knew every measurement that counted as a vector. Energy isn't one. It's kind of like time. It's a scalar. All of these energies here, even though we plugged vectors into the formulas, velocity is a vector, height is a vector, even though we plugged vectors in, each individual energy total comes out as a scalar. It doesn't care about direction. If I give something 10 joules of kinetic energy, the energy doesn't really care what direction it's moving in. It just cares energy, go. And that's why here in the slide, even though our height, the height we'd be descending as you slide down the slide, is in the vertical axis, and the velocity is slanted, that doesn't actually matter. Because they aren't vectors. They don't have to be in the same axis anymore. Energy is a scalar. You can't have 10 joules pointing upwards because no form of energy points anywhere. It's just energy. It relies on something else to direct whatever happens as a result of having that energy. You could slide down this slide, or you could just jump off of it. Making that choice, like the energy is still going to transform, the GPE is still going to be released, but making the choice of whether to just drop off or use the ramp changes the direction of the velocity, but it doesn't have any effect on the energy change. I feel like I'm rambling a little bit. I apologize. We will do the math for this type of question in full next time. That'll segue us into looking at how friction interferes with things. But right now, the main takeaways that I want you to consider is for any object that's rising, KE turns into GPE. For any object that's falling or descending, it doesn't even have to be falling, GPE turns into KE. And since no form of energy is a vector, direction of the vectors you plug in doesn't matter. Because within the KE and GPE formulas, each of these formulas involves multiplying a vector by another vector, and that kind of just makes all the direction vectors involved cancel out. In the KE formula, you square the velocity. That gets rid of its vector direction because that's a vector times a vector. And in the GPE formula, you multiply an acceleration times a displacement. That's still two vectors being multiplied together. That gets rid of its direction as well. So none of these energies have direction, and that's why the axis of the velocity in the slide question doesn't matter. Cool, uncool questions so far? All right. It's 10:15, and it'll take more than 5 minutes to do any of this math, so we'll save that for next time and use it as a segue into a related example. Well, no, Friday will be test day, so probably next Monday. Sorry, let me reiterate. Friday's the day we talk about the test you just took. There's not a second test. Keep all my words clear. Whenever we continue learning, we'll pick up with this example and fill in numbers. Anyone need anything before we break? All right. If not, not, have a good day. No lab this week. Stay warm and dry. It was raining as I came to work.